Hello, this is Mr. Troha, and this is our third video about the sun. We're going to be talking about solar fusion and the sun's interior. If you didn't know it, the sun generates energy, a lot of energy. Actually, in 1 second, it produces more energy than the Earth did in 3 million years. And we get only a small fraction of the energy that it produces. We get a lot of it in visible light, which is great because we can see things, but we also get all the other different types of light along the electromagnetic spectrum. So some of you might remember ultraviolet, that's where we get our sunburns, but even, microwaves, television waves, radio waves, all these things are coming from the sun to us. So how much energy does it produce? 4 times 10 to the 26 joules, if that number would even, compute. It's so huge. But that's how much is produced by the sun every second. We only receive a small bit of that where we are, and the total amount of energy that the world produces, when I look this up, 4.4 times 10 to the 9th joules. That means we would have to produce, as far as humans, we would have to produce energy for 3 million years to match what the sun can do in 1 second. So how does it do all this energy? Through fusion. It'd be great if we could do some fusion here on Earth, but it takes very high temperatures, and it's going to be we're going to be looking at the nuclear fusion a little bit. This is an image of how it does it on the sun, but I'll get a little more specific here. So what actually happens? We have these smaller mass atoms, hydrogen and helium, which combine together. And when they combine together, the mass of the new atom is actually less than the combined masses of the two smaller ones that joined up. That missing mass gets converted into energy. That big equation on there, E equals mc squared, everyone's heard about it, but probably don't really know how it's used. But that m is mass, c is the speed of light, and E is energy. Mass and energy have an equivalence. So let's get specific into that nuclear fusion stuff. It's called the proton-proton cycle, and it actually starts with 2 protons. A proton is the nucleus of a hydrogen atom. So this H with a 1 on it means it's hydrogen. It has 1 proton in there and 0 neutrons. So 2 hydrogens run into each other. This has to be moving very quickly and very hot to make that happen. They combine and they create a hydrogen atom with a neutron. It's now one of the protons expels some things, becomes a neutron, and so I believe it's called deuterium is what that hydrogen is called. It also expels a few other particles, neutrinos, positrons. Now, one of those runs into another hydrogen and forms into helium. Helium now has 2 protons and 1 neutron, and it releases a gamma ray photon. The gamma ray photon starts its process of ultimately leaving the surface, and that's how we get our light. These 2 heliums combine together into a stable form of helium, the one that we would think of with 2 protons and 2 neutrons, and it now has 2 additional protons that are being sent off, and it kind of continues that cycle again, goes back to the beginning. All right, so a very small amount of mass is actually converted into energy, but that small mass can create lots and lots of energy. In fact, but interestingly, in order for the sun to be the color it is, and we can tell how hot it is based on the coloring and things, it has to produce 600 million tons of hydrogen must be fused into helium every second. And hydrogen is not very heavy, so 600 million tons of it is a lot. I want to talk for a second about how this energy gets to us. There are 3 types of ways that energy can be transferred. Conduction is hot, right? When you touch something that's hot, it transfers energy. Or cold, it's transferring energy from you. Convection is moving fluid. We talked a little bit about convection in the last video. and then radiation is by photons of light running into things. Talking about this because we need to talk about how does the energy get from the core. The core is where the energy is created. It's in the core that the hydrogen is fused into helium and we get that energy. It's very, very hot, 15 million Kelvin. The next layer of the interior is a radiant zone, and that's where the energy is moving outward. It changes temperature from the core towards the outer edge of the radiant zone. It goes down from 15 million to about 2 million. And along that time, that's where these photons are running into each other and trying to reach the surface. Then we have the convection zone. As those two zones tell you, the radiant zone is the movement of photons passing energy. The convection zone is going to be convective gases moving, the less dense moving out and the more dense falling down. So rising up to the surface of heated gases moves energy outward, and you can see the temperature goes from 2 million to a cool 6,000 Celsius as it gets to the surface. So as I said, fusion happens in the core. It's been happening for 5 billion years. That's about what we estimate the sun is, and it's going to continue for 5 billion more before our sun dies and goes away. Now, an amazing thing is when one of those gamma ray photons is created, it takes 10,000 years for it to go from the core through the radiative zone to the convective zone. So 10,000 years to get through the radiative zone, and that's because it is bouncing from particle to particle to molecule to molecule, and every time it bounces, it loses a little bit of energy. So in the convective zone, it now takes hundreds of years to then get to the surface, and once it leaves, it only takes about 8 minutes to get to us. So I talked about how those particles bounce. These little green arrows represent that. It's formed and bounce, 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 right, until it gets to the convective zone. But it bounces for 100,000 years. So the energy moves to the surface from the core, as I said, by radiation and then by convection. As I mentioned, all life starts as a gamma ray photon, but every time it bounces, it loses a little bit of that energy. And so if you look at this picture of the electromagnetic spectrum, the gamma ray is over here. It's a very short wavelength, very high frequency photon, and every time it bounces, it loses some of that energy. Down here on the other end, where you see radio waves, that's the lower, very low energy waves, and so it moves from this gamma ray, depending how many times it bounces and loses energy, X-rays, ultraviolet, visible. So obviously a lot of light coming in the visible spectrum from the sun. So it's lost a lot of energy along the way. So we mostly get, we get a lot of the visible light, right? These colors of the rainbow here, the spectrum. Notice what this graph is showing is that the higher up it is, that's the higher the wavelength is, or the type of wavelength we're getting from the sun. So we're getting low on the ultraviolet. This is all visible light, and then infrared, and we're getting very small amounts of all these other types. Okay, so that's a little bit about fusion and the interior of the sun, and I hope you are enjoying this unit.